Hello everyone, welcome back to Solid State series. This is the Solid State part 18, and in this video I'm going to discuss the structure of cesium chloride. Structure of cesium chloride. In the previous videos we discussed four different structures. One is the NaCl type, second one is the zinc blend type, third one is calcium fluoride, and another one is Na2O, sodium oxide. These are the four structures we discussed in the previous videos, and in this video I'm going to discuss the structure of cesium chloride. In fact, the structure of cesium chloride, if you observe here, there are two different possibilities. Two different possibilities in the sense, here one is a cesium cation, another one is chloride ion. And there are two possibilities. The first possibility is here chloride ion may form simple cube. Simple cube means the particles are present at the corners. In that situation, cesium ion will occupy cubic void. Cubic void is present at body center in a simple cubic unit cell. Already we discussed in the previous video. In the first option, chloride ion may form simple cube, and cesium ion will occupy what we call body center, which is actually a cubic void. And the second option is cesium ion may form a simple cube. That means cesium ions are present at all corners of the cube. Chloride ion will be at a body center. These are the two options, but here we will be studying this structure by fixing the position of chloride ion. But already I cleared that point. There are two options here. Cesium ion may form lattice, otherwise chloride ion may form lattice. Which lattice? A simple cube. And what is the position of counter ion means? Obviously that is present at what do we call cubic void. In fact, body center is a cubic void in simple cubic unit cell. So let us discuss the structure of this cesium chloride and cesium chloride type structure. Cesium chloride. And in this, I am assuming chloride ions. So chloride ions are forming simple cubic lattice. Chloride ions form simple cubic arrangement. So they will be present in a simple cubic arrangement. That means they occupy all corners of the cube. And cesium ion occupies cubic void. In fact, cubic void is present at a body center. Already I cleared the point. Instead of this combination, reverse is also possible. Reverse is also possible, right? And here, but we are developing the structure of cesium chloride by taking one assumption, that is chloride ion is forming lattice, a simple cube, and cesium ions are occupying body center. In fact, that is a cubic void. And here chloride ions are at all corners and cesium ion is at a body center. This is the only point you need to remember. And based on this, remaining properties of this solid can be developed spontaneously. Now you see, if you take one unit cell of cesium chloride, totally there will be 9 ions. This is not effective number of ions. Total number of ions 9. How total number of ions 9? Because 8 chloride ions are present at 8 corners and 1 cesium ion. So 8 plus 1, that is 9. Total number of ions 9. But in fact, for every calculation, we need a Z effective. For every calculation, we need Z effective. So effective number of ions, if you find, so chloride ions are present at corners. So 8 corners, contribution of corner particle is 1 by 8. So effectively, there is only 1 chloride ion. And cesium ion is present at a body center. There is only 1 body center and the contribution is 1. And it will become what we call 1 cesium ion. So even though there are 9 ions totally, effectively there is only 1 ionic pair. 1 ionic pair, that is 2 ions. So 2 ions, that is actually 1 ionic pair. And based on that, we can easily find the mass of the unit cell. But in the examination, 100% they will provide the atomic masses. So cesium atomic mass we cannot remember. Definitely they will provide. And the mass of each unit cell, the mass of one unit cell, if you take, there is 1 ionic pair. So cesium mass is 133 and chlorine mass is 35.5. So 133 plus 35.5, that will be 168.5 AMU. But that is the mass of one unit cell, right? Mass of one unit cell. But if you want to find the mass of 1 mole of unit cells, 1 mole of unit cell's mass in grams we are finding. So you need to take two modifications. The first one, this must be multiplied by Avogadro number. This value must be multiplied by Avogadro number because we need the mass of 1 mole of unit cells. So Avogadro number. And I'm expressing the mass of 1 mole of unit cells in grams. So I have to convert this AMU mass into grams. So that should be divided by Avogadro number because 1 AMU is equal to 1 by 6.022 into 10 power 23 grams. So now it will be converted into grams. And here Na gets cancelled and it will become 168.5 grams. So 168.5 AMU if you take, that has only one unit cell, but if you take 168.5 grams of cesium chloride, if you take, no doubt there will be 1 mole of unit cells. So very clear, number of unit cells present in 1 mole. 1 mole of cesium chloride means it's a formula mass. Formula mass of cesium chloride is 168.5. So 168.5 grams will definitely have what do we call Avogadro number of unit cells. And the most importantly, the coordination number of a cesium. Coordination number of a cesium and coordination number of chloride. But we'll talk about this coordination number with the help of diagram. But now we have to find the edge length of cesium chloride unit cell. And see, this is the body diagonal I'm taking. This is a body diagonal. This is a body diagonal. So what are the positions? What are the points present on this body diagonal? This is the corner. This is the corner. And this is body center. In fact, body center is a cubic void. And cubic void is actually occupied by cesium cation in our discussion. And the corners are occupied by chloride. So here, this point to this point, that is root 3a. Body diagonal is root 3a, and that is equal to 2 times of radius of cation plus radius of anion, because this is radius of anion, this is radius of anion, and here this is the radius of cation 2 times, and this is the expression. And edge length in terms of both cation and anion, if you take bring this send this root 3 opposite side, you'll be getting the edge length. All right. And packing fraction, if you calculate very clear, packing fraction means the volume occupied by all ions present in the unit cell divided by the volume of unit cell. See, there is one ionic pair effectively in one unit cell. Effectively one ionic pair. That means one cation and one anion. So volume of cation is 4 by 3 pi r c cube. Volume of anions 4 by 3 pi r a cube. There is only one cation, one anion, and 4 by 3 pi is common. And here, obviously, cubic unit cell, volume of cubic unit cell is a cube, and here this is a cube. But if you can recollect, in this discussion, I already told you, so chloride ions are forming lattice. Which lattice? Simple cube. If you can recollect, in case of simple cube, the particles which are present at the corners are in contact. So this is a corner particle, and this is a corner particle, and here these two corner particles are in contact. These two corner particles are in contact, and there is a contact, and through the what do we call edge, through the edge, and this A is equal to edge length. A is equal to 2 times of radius of anion. Very clearly in the first video of ionic solids, I mentioned one point: for all ideal calculations, we are making these assumptions. In reality, there may be some gap between what we call anions to accommodate cesium ion. So the chloride ions may move slightly in opposite direction. There may be a slight distortion, but for ideal calculations, paper and pencil work, we always assume that there is a contact between chloride ions because chloride ions are forming simple cube. Whenever a simple cube is produced by a particular particle, they will be in contact along the edge. The particles will be in contact along the edge. And here, based on that edge length, A is equal to 2 times of radius of anion. And here, if you substitute and if you simplify further, you'll be ending up with this expression RC by RA whole cube. And in fact, cation is occupying cubic void, and the radius of cubic void is 0.732 times of radius of particle which is forming the lattice. So this radius ratio is 0.732, and finally if you simplify you'll be getting 0.728 packing fraction, 72.8 percentage. I told you, in reality, there may be some gap. To accommodate this cation, these anions will move in opposite direction. There is what we call some gap between what we call anions, but for all ideal calculations, we assume that there is a contact. Here there is a contact, but here this particular diagram is to explain what we call coordination number. See, this is CCM ion. According to our discussion, this is surrounded by 8 ions. So CCM ion is surrounded by 8 ions. 1, 2, 3, 4. And in this diagram, you can see easily here 1, 2, 3, 4, 5, 6, 7, 8. And what is the distance between body center and a corner? Distance of closest approach, whatever it may be. If you say distance between cation and anion or first nearest neighbor distance, anything it can be, that is half the value of body diagonal. So body diagonal is root 3a, root 3a by 2. And similarly, if you are focusing on chloride ion, which is occupying corner, it is surrounded by 8 body centers, because corner is common for 8 unit cells. And here in this diagram, I have shown 1 unit cell. Like this, it is surrounded by 8 body centers. Hence, coordination number of cation is 8. Coordination number of anion is also 8. And the packing will be 8:8 type of packing. The packing is 8:8 type of packing. And if you take the slice view, so after equal sharing, the corner particle is shared by 8 different unit cells. So here this is the slice view of this ionic solid, and this is about the structure of a cesium chloride. And once again, and the cesium chloride structure, if you take, there are two options. Cesium ion may form simple cube. Chloride ions occupy cubicoid. Otherwise, chloride ion may form simple cube. In that situation, cesium ion will occupy cubicoid. And this is the end of the structure of cesium chloride. Thank you. Thank you very much.